Hi folks, welcome back to Physics with Captain Rod. I'm going to talk with you a little bit here about numbers 13, 14, and 15 on your homework over electromagnetic waves and atoms. So number 13, let's see, it says a photon with an energy of 2.6 EVs is absorbed by a hydrogen atom. So we've got a photon coming in and the energy of that photon given in the problem 2.6 EVs. So I'm going to let this picture here represent my hydrogen atom with my nucleus and my electron going round and round. And the first question is, it says find the minimum N for a hydrogen atom that can be ionized by such a photon. Well, remember that the electron energies for a hydrogen atom, in class we built a little table for this. It was minus 13.6 EVs, minus 13.6 over 4 EVs, minus 13.6 over 9, minus 13.6 over 16. Again, these are some values here. I'm just going to write them down in fraction form. So the minimum value of N is the value of N over here, like this is N equals 1, N equals 2, N equals 3, 4, actually this one's 4, and so forth. You know, if you look at the N equals 1 here, it's going to take 13.6 EVs to ionize that. This isn't anywhere close to 13.6. Then look at this one and say, is this enough? And then if not, look at this one and say, is this enough? And in the end, you're looking for the value of N where this number is enough to ionize it, meaning that this number needs to be bigger than whatever these energies are. Part B, where it says find the speed of an electron released from that state when it's far from the nucleus. So once you determine the N, and I'm not going to say which one it is, but once you get what value of N here, the difference in energy between this and whatever this number is, or whatever this number is, depending on the value of N, is going to be carried away by the photon. You know, so, or I'm sorry, by the electron. That's because this photon comes in carrying the energy of the photon. This electron leaves. It takes whatever energy it does that you find to ionize it, and then the energy that the electron carries is going to be the difference between the ionization energy and the energy of the photon, of the incoming photon there. Take that energy, it's going to come out in EVs, and convert it to joules, and then take that energy and set it equal to 1/2 mv squared, where the m is going to be the mass of the electron and the v will be the velocity of the electron. So that should be enough to get number 13 finished up. So let's go ahead and talk about 14. Before we do, I'm going to get rid of this stuff. All right, number 14, it says U.S. Navy has long proposed construction of extremely low frequency waves, or extremely low frequency communication systems. My apologies, late day here. Such waves could penetrate the ocean to distant depths. Calculate the length of quarter-mile wavelength antenna for a transmitter of frequency hertz. Let's see, calculate the length of a quarter wavelength antenna for a transmitter generator waves of frequency hertz. Well, for starters, we know we're dealing with a frequency of 70 hertz. And you can convert that to wavelength from C equals frequency times wavelength, where this value is your frequency, this is the speed of light, 3 times 10 to the 8th meter per second, and it's just a matter of calculating the wavelength here. Now I think when it says calculate the length of a quarter wavelength antenna, I guess they mean calculate the length of a quarter wavelength antenna. I guess they mean that the length of the antenna is 1/4 of that value. That's what I suspect, that's what they're looking for there. And then they're asking you to comment on practical or not. That's enough on 14. Let's talk about 15. So 15, it says a distant star is approximately 9.32 times 10 to the 18th. 2 meters, oh, pardon me. Okay, that's a distance. And it says, if the star were to burn out today, how many years would it disappear? So let's imagine that here's the star. It's a happy star. It's giving light in every direction. And, you know, we're on Earth, way out here. And it takes light from that star to travel this distance right here a long, long, long time. When the star quits giving light, what's going to happen is there'll be kind of a gap here. For a long, long, long time, you know, if this thing stopped giving light right at this instant, we would still see light traveling for quite a while. That's because it takes a long time for light to get from this star to where we are. This is just a basic distance speed problem. Speed is distance over time. The distance is given in the problem. For the speed, use the speed of light, c, 3 times 10 to the 8th meter per second. And that should allow you to calculate a time in seconds. I see that the answer says to calculate it in years. Okay. Part B, where it says, how long does it take sunlight to reach the Earth? So for part B, you're going to have to look up the distance from the Earth to the Sun. Same formula here. You're going to put that distance here, use the same value, 3 times 10 to the 8th meter per second, and then calculate t. Looks like they want you to then convert it to minutes. Part C, how long does it take microwave radio signal to travel from the Earth to the Moon and back again? All right, so let's imagine, you know, here's the Earth, here's the Moon. So they're asking for the time it takes a signal to travel from the Earth to the Moon and back again. So the actual total distance there is 2d. Look up this distance, and the total distance traveled by the light waves is twice that distance. And then we're going to use this formula here, that the speed is equal to distance over time. Use twice the distance between the Earth and the Moon here. For the speed, you're still using the speed of light. Even though it's microwaves, it's still, you know, an EM radiation. All electromagnetic radiation travels at 3 times 10 to the 8th meter per second. So put that value here, solve for t. So that should be enough. I think we talked about most all the other homework problems the other day, so hopefully you're working that over the weekend. You're going to have your quiz on Monday. You know, make sure you have a good weekend, and we'll see you on Monday, folks. Bye.